So to get that idea, we are just discussing the static timing analysis. So what is exactly mean STA, and why timing analysis is very important in the design circuits, in digital circuits. What happens if we don't meet the timing analysis? Okay, what happens if we don't meet the timing specification, whatever the given by the design engineers? So all the things we'll discuss. Okay, different topics in the static timing analysis. Okay, so can anyone tell me first, why is timing analysis, why we need to perform the timing analysis? Is it very critical to meet the timing specification according to our design spec? What happens if we don't meet the design, whatever everything they will give at the time of whenever one project is going to develop. Okay, at starting only we will get all the specification regarding the design of the circuit. Okay, design of the project. So at the starting time only, they will give a specification at what time the power specifications, and area of the silicon chip, within how much area we need to reach our design, what is the technology we are going to use, and what is the nanometer technology we are going to implement in our design, and what are the timing specification, at what frequencies our design have to implemented, at what frequency the design need to run. Okay, and what are the frequency we have used the before project, what speed we have used before, and how much speed we can get the present project. Okay, all the things, the processor wise, the generation wise, everything at the starting only, they will give the everything in the specification. According to the specification, we need to reach our goals in the design. Okay, in our current project, so that according to the power consumption and area of the chip, and also with the respect to these things, so we are going to check the timing analysis also very critical compared to the low power analysis. Okay, low power verification and area of the chip. Okay, so clock should match with the specification. Yes, okay, because whatever the processor frequency has given in the specification, we need to reach that frequency. Okay, how we can reach those frequencies means by using the timing analysis. If we don't reach the certain frequency, or if we are seeing any faults in the circuit, any clock faults in the circuit, all the things we can check with the static timing analysis. Okay, so uh, let's recollect the digital things. Already last week we have discussed all the digital topics, right? Today we'll discuss the delays of the digital electronics. Also last week we didn't discuss the digital electronic delays, combinational logic circuit delays and sequential logic circuit delays, right? Today we can discuss. And content of the static timing analysis, mainly what are the things we are going to cover. Okay, mostly we won't cover very advanced level things, we will cover the student level things. What as a verification engineer, no need to know all the things in the depth. Okay, we are going to learn overall things, exactly what is meant by static timing analysis and what are the main things, and we will do the some problem statements in the timing analysis. Okay, so these are the content we are going to cover. What is the timing analysis, and what are the different types of analysis are there, and what is the STA design flow? That means where can we perform the STA, where we can perform. Okay, like we have the VLSI design flow, right? A front end design and the back end design. So STA, in which step we can perform, like that. And timing parameters, different timing parameters like arrival time, required time, slack, slew, critical path, setup time, hold time, analysis, everything. And static timing analysis process and methods to improve the timing. How can we improve the timing? and the practical examples and the solutions. Already we have shared the digital logic design questions, right? Mock tests, every questions we have shared. In that static timing analysis also one particular topic, right? Nearly 20 plus questions are there, interview questions. So to do those questions, we need to know the static timing analysis concept, so that it will be very easy for you to do solve those problems. Okay, so once we discuss these things, you can go through those questions and you can solve the problems. One or two questions we will discuss in the session. Okay, and next, why what is the timing analysis mainly? So, what is the timing analysis means? As I said that if you want to manufacture a processor, we need to go through some of the important constraints. Okay, important constraints are nothing but in terms of area, in terms of which technology we are using, which nanometer technology or which silicon technology we are using. Okay, in terms of power consumption, or every time we need to check for the power consumption, low power consumption, low power consumption. When we will get the low power consumption, internally there are so many techniques for the low power consumption. Static timing analysis also one of the main solution for the low power consumption. Why? Because by using the static timing analysis we can check every logic path. Okay, in the digital logic circuit, if you take any digital logic circuit, there will be several parts. Okay, like this is one path and this is second path. From this here third path, like that there will be so many parts. Okay, in these parts also there are some timing which are not necessary. Okay, there will be some parts which are not necessary. If you use those parts, what happen? The power consumption will be more. Okay, so if you avoid those type of parts here, we can reduce, we can delete those gates. Okay, by deleting those gates there will be no wire or there will be no internal connections and there will be no gate. Okay, so that we can reduce the power consumption. That is one of the main factor we need to check. And also timing analysis. Okay, so timing analysis is nothing but for both combinational logic circuit and also sequential logic circuit. For both circuits we will check, because for both circuit there will be different type of delays. Okay, different type of delays involved in the combinational logic circuit and also sequential logic circuit, right? So by using those delay, whether our design is meeting our timing specification or not, we need to check for that. Okay, suppose if you see here, we are considering the two different type of processors in our laptops. Okay, one is a Intel core. You can take a Intel processor or a AMD Ryzen processor or Qualcomm Snapdragon processors in our mobile phone. Every processor you can compare with the any processor. It is a 5 nanometer processor and 128 bit. Okay, it is also a 5 nanometer processor and 128 bit. Okay, both in the technology wise, in the nanometer wise, in chip area wise, both are equal, and in the memory wise also both are equal, 128 bit, 128 bit. But here coming to the frequency is nothing but speed. Okay, we need to check for speed also, right? How the systems are working, in which speed those are working, we need to check. So here it is working 4.4 gigahertz frequency, but here it is working 4.8 gigahertz frequency. There is much difference in the frequency. So obviously which processor we will pick as a market, in the market, which processor we will pick? Mostly 4.8 gigahertz frequency, because this is the high speed processor. Mostly we will go for high speed processor. Mostly the cost will be also same. Okay, only because of speed the cost will not reduce. Okay, both cost will be same, but we will prefer the high frequency processors, right? So according to the market requirement, we need to reach our goals in terms of speed also. In terms of speed is nothing but in terms of timing. Okay, if every timing is perfect in the digital electronics, speed automatically increase. If we don't meet the timing specification in our design, the speed automatically reduces, right? So we will consider the 4.8 gigahertz frequency. So that we need to check in every point to point where we can meet our timing specification. Okay, so this is the what is meant by timing analysis. Next one, what is the requirement of the timing analysis? What is the requirement of the timing analysis? So as I said that, suppose if two systems are there, okay, if two systems are there, which system can be preferred? Suppose if the design is not operating at a expecting range, for some of our processor they have given the expectation range as a 5 gigahertz. Some processor they have given expecting range as a 5 gigahertz, but it is reaching reality, it is reaching only 3 gigahertz frequency. Okay, so if the frequency, if the design is not operating at the expecting frequency, expecting range, in this case we need to change the few things in the design. Okay, we need to change the few things in the design so that the timing can be improved and meet our expectations without any changing in the functionality. For reaching the timing, we no need to change any functionality of the design. Okay, functionality in the sense exact design operations, whether it is a memory or it is a core or it is any IO blocks. Okay, no need to change any functionality. There are separate techniques for the timing analysis. Okay, nowadays we are using the tools also. By using the tools also, we are checking the timing. Okay, so that we can improve our timing functionality without changing any functionality. Okay, so what is mean by timing analysis? Actually, timing analysis is nothing but it is a methodological analysis. It is just a method to analyze the design as per the time. Okay, so it is a one method which is used to analyze a digital circuit if the timing constraints defined in the specification are met. Okay, whether it met the timing specification in the design or not. Okay, so for that purpose we are using the timing analysis. Did you understood everyone up to here? Did you got the point why we are meeting the timing specification? Why it is very important for timing analysis? Everyone got the point up to here? Which tools are using, we'll discuss the tools and all, we'll discuss. Just every company have different tools. Synopsys have different tools, Cadence, Intel, those are internal tools. I also don't know what tools. Those are some STA related tools. Our normal tools can't use Quest or Model Simulator. These tools can't be used. Those are separate tools for static timing analysis, mainly for timing. Those are separate tools. Any open source, we need to check. For open source, we need to check. Okay, any doubts, others? No doubts up to here. Okay, next one. So, different type of timing analysis. First one is dynamic timing analysis. There are mainly two types of analysis. One is a dynamic analysis, another one is a static analysis. Okay, so what is mean by dynamic analysis? If you see here, it is used, dynamic analysis is used for testing for UVM, our like in SDA things. UVM is not related to this. It is STI is different, UVM is different. UVM we are using EDA playground only. UVM we are using EDA only. Otherwise we can use the model simulator also. Vivado tools also we can use. EDA tool also best tool. As you are learning now, as you are a fresher, no need to go for those tools, because as a design verification engineer, every tool is same. If you go to physical design, then the tools will be very different. You need if you go for physical design, you must work on the design tools. tools, because everything will be depend on the tool. But as a verification engineer, everywhere any tool, it is same only, because wherever we need to write the code, we need to check the output, right? Coding and simulation, everywhere it is same only mostly. But if you go to industrial tools, what happen means you will work on Linux commands mostly. Through the Linux commands, we will write there through the scripting language. We will do the like we'll run the codes. We'll run through scripting. But as a learning, no need to go for tool. Okay. But if you are interested, you can download the Vivado tool. We'll check any tool available for UVM. So in the lab session, we can discuss the UVM. Okay. Okay, next coming to the dynamic timing analysis. So it is mainly manual, like a manual in the sense we will just apply the stimulus, and we will apply the clock frequency, certain clock frequency. Based on that clock frequency, we will monitor the output. That is mainly dynamic analysis. So dynamic analysis testing detects and reports internal failure the instant they occur. This makes it easier for tester to precisely correlate these failures with the test actions for incident reporting. Mainly, it verifies the timing of the circuit by applying the stimulus. You know how the DUT, there will be a DUT, nothing but design. For the design, we will apply the stimulus through the test bench. With respect to this, we will apply the some clock frequency. Okay, some certain range of frequency we will apply, so that um, we will get the we can monitor the output. Okay, so it can be verify the design or functionality by applying the stimulus to the design. If you consider any design, like there will be any design, like there will be several inputs and outputs like this, right? In order to verify these signals, we need to generate a test bench. Okay, that can generate the stimulus and can monitor the output of the design. During the dynamic timing analysis, the design is supplied with the clock here, which is nothing but with a desired frequency. Suppose 250 megahertz frequency. Okay, based on the timing, we can generate the clock, right? So that we can generate the clock at working at the desired frequency. Okay, so there are different advantages and disadvantages with the dynamic analysis. Okay, so coming to the advantages of the dynamic analysis, or it is a very accurate for the spice level. You know, the spice in a digital, we will connect one circuit to another circuit in a CMOS level. Okay, that is nothing but the spice level, right? In the spice level, it will work very good, and it permits you to validate the static code analysis finding, and it can be conducted for against any applications. Okay, we can use for any application, and it provide these tools provide the flexibility, and there will be some it identifies the runtime environment also, like whatever the failures are there in the runtime, those failures, it can be analyzed. And simulators also available for the dynamic analysis. There will be simulators also. And vector generations, vector generations means suppose if you take any input stimulus, any input if you take, there will be 32-bit data, 64-bit data in the output side, right? So vector generations take too long time. Okay, because the design contains various combinations. 32-bit means 2 power 32 number of bit combinations will be generated. It should generate those many combinations, right? So we may not able to cover all possible combinations, so that's why it is a incomplete, we can tell as a incomplete. It requires the more memory, so to generate all the things, it requires the more memory CPU resources compared to the static timing analysis. Okay, so this is what the dynamic timing analysis. While simulation, yeah, when we are writing the code, test bench code, there only we will give the stimulus to the DTS. Stimulus is nothing but giving the inputs, right? We will generate the stimulus in the test bench. At that time only we will give the uh, dynamic analysis with respect to the certain frequency. Okay, like we need to frequency, we know how to check the frequency, right, for a given clock, so that we can generate the frequency, and at certain frequency we can give the input stimulus. Next one, we can give in the middle. Yeah, we can change in the middle also. It will work under runtime environment also. It identify the changes in the runtime environment also, so that we can give the middle of the there also. Okay. Next one, static timing analysis. Why we are using the static timing analysis mainly? Mainly the static timing analysis. Why? Because the timing analysis, it is which is carried out independently. Okay, it works independent manner. The input will work independent manner, so that we are using the static timing analysis mainly, and it detects the based on the tool consideration. Okay, maybe if it have any defects in that sense, a false path, multiple cycles, like that, it will detect the everything. So we will analyze the time in each path without application of the input. Okay, in static timing analysis, each and every path we are going to analyze the separately. Suppose for one output there will be different number of parts. One path is getting from this, and one input is getting like will have different outputs, right? So different parts will be there, so each path will be checked in the static timing analysis. Okay, the main goal of the static timing analysis is to verify whether signals will arrive neither it should not arrive neither early nor late. Okay, it should arrive at the given frequency only. It should not arrive too late or too far, too early. Okay, and hence a proper circuit operation can be ensured. Otherwise, we cannot ensure the proper circuit. Okay, because the signal should not arrive too early or too late, right? At the given time, it should reach. Because suppose if you take any example, like what happens, suppose if you take any example like a bus accident or a train accident, if you take so whenever the train is moving or any bus is moving, if the brake is not applied properly, okay, in the time, in particular time, if the brake is not applied properly within fraction of seconds, the vehicle total damage will be happen, right? Within fraction of seconds, if it not reach the output, if brake not reach. Okay, so that those type of incidents will be happen. Suppose if it not work within fraction of seconds, it not reach means total design will be uh, work, like because there will be dependency. Okay, one output will be dependent to another block diagram, and one block will be independent to the another block, right? So if any block doesn't reaches the time, given time, every it will be affect to the every block internally. So that timing requirement is very important. Okay, so mainly advantages of the static timing analysis are faster. Okay, these are very fast. Like a dynamic analysis, if you take, that is a manual thing, right? If you have 32 bit 2 power 32 combinations, it cannot generate. Middle of that, it may skip all the combinations. Okay, but static timing analysis is the faster. Okay, in as we seen in the DTA, it is not like that, and it will use it to validate the each and every path. We can validate every path. Okay, so this is mainly static timing analysis. So if you see the static timing analysis here, suppose here this is a one flip flop, one flip-flop given to the one input, here also one input. Here different paths are there. This is one path to the output, and this is the second path to the output, and also this is the third path to the output, and here fourth path, fifth path. Okay, different path out there. Okay, so the propagation delay. Can you tell me what is mean by propagation delay? What is mean by propagation delay? Propagation delay is nothing but, suppose here at 5 time units I have given the input. Okay, but here the output I am reaching at the 50 time units. Okay, or at 100 time units, but middle what is happening? Middle some functionality is happening. Every functionality, it requires some time. Okay, even this flip flop may require some 10 time unit time. This wire may require 1 time unit delay. This gate may require 5 time unit delay, and this gate may require 10 time unit delay. So all internal delays will be calculated, and after all internal delays will get the output at particular delay at particular time. Okay, so propagation delay is nothing but it can be defined as the minimum amount of duration for which you can wait for getting an output from the logic circuit after applying the input. Okay, so that is the propagation delay. Even though it is the longest path, the path is never affecting the output. Okay, suppose this path is there. If this path is not affecting the output, that will be good. If that path is affect the output, it is not a correct path, we can call it as a false path. Okay, so false path is nothing but which can be affect the output. Okay, so we'll see clearly what is mean by false path and all. Did you understood what is mean by propagation delay, everyone? Propagation delay is nothing but the internal delay after giving the input, at what time the output is getting. Internal delay is nothing but propagation delay. Okay, clear up to here? Static timing analysis is very confusion, and it is very difficult to learn also. You can't remember in a single session. More delay treated as a propagation delay only, but we cannot directly go to that. If any more delay get in particular circuit, we cannot confirm that is the propagation delay. We need to check whether the path is really working or not. Okay, if we got the more delay, we need to check whether we are using that path in our circuit or not. Okay, we cannot blindly tell that is the propagation delay. Okay, so now we'll see. So these are the limitations of the static timing analysis. Okay, complex to the design and understand. Static analysis is very complex and it is very difficult to understand. Okay, and next, good for synchronization circuit. Mainly, not only for asynchronous, it is mostly good for synchronous circuits. And these are the difficult to handle few cases. What are the few cases? Multiple clocks. If you have multiple clocks, a circuit is depending on the multiple clocks, so that is difficult to handle, because one flip flop is working at the clock 1, another flip flop is working at the clock 2. These flip flops are connecting with each other, so that time multiple clock is somewhat different. And false path, there will be false path, the true path in the circuits. Those things we need to identify, otherwise we will get mistake. Multiple paths, okay, multi-cycle paths, those things we'll discuss now. So first one, false path. Okay, I'm taking the two multiplexer design here. For 2 by 1 multiplexer has a selection lines, two inputs, and one selection line, one output. Okay, so here I'm considering, suppose here there is a selection line. in this selection line, I didn't give a same selection line. Like 0 means it applied both the zeros. 1 means it applied both 1. So how many combinations we will have? This is one combination and this is second combination. Okay, or third combination. Total 4 combinations we will have. Okay, but if you see the total 4 combinations will be there. Suppose we'll take some delays. Here I am taking some delay, and here this input I am taking some delay. This delay will be the 100 nanoseconds, and this delay will be the 50 nanoseconds, suppose. And here this delay will be the multiplexer delay will be the 20 nanoseconds, and here there will be 2 path like this, right? So this delay I am considering as 100 nanoseconds, and here I am considering this path as 50 nanoseconds. Please listen carefully. 50 nanoseconds, and multiplexer is 20 nanoseconds. So how many path will be there here? First, can you tell me what is the propagation delay here? Anyone? What is the propagation delay? Propagation delay is nothing but high, whatever in compared to these, there are 4 paths here. 4 different paths are there. In 4 different paths, which path have the highest delay? We can tell that that is the propagation delay. So, what is the propagation delay here? 190. Okay, which one? Can you tell? Which path? Suppose we will consider here to here. What is this? 100 plus 20 plus 100, 200, 220, 240. Okay, 240. Next one, this 50 plus like this. 50 plus 100, 150, 170, 190. And next here, both are same only. 100 plus 50, 150, 20, 170, 190. And next here 50 plus 20, 100, 140. So what is the propagation delay here? 240. 240 is the highest path, right? Mux 1 is a 20. Input of mux 1 is 100. So I am considering this here. This is 100. Here also 100. 100 plus 100, 200, 20, 20. This is also possible, right? If selection line is a 0, 0, what happened? This will be the 0. So this input will get at the output side. Here also 0. This input will get at the output side. So here the propagation delay will be the 240. Okay, 240 is the propagation delay. Everyone understood? Everyone understood? Suppose I am taking, suppose here in the selection line I am using the NOT gate. I am using the NOT gate. If I use NOT gate, what happen? The selection line is 0, and here it will be 1. Okay, here 1 means here it will be 0. Like that the combinations we will get. Okay, so here can you identify which one is the false path? Which one is the false path and what is the propagation delay? Can you join for the next session quickly, everyone?